All right, good morning, folks. We are here on Tuesday, and it is February 12th. Is that right? Huh, maybe that's right. No, it's the 11th. All right, February 11th. So we have a couple of things to work out here. It's Tuesday, so that means homework is due tomorrow, and that means it's tomorrow by midnight. PLC one, there have been a couple of you who haven't turned in PLC one. I highly encourage you to stay on top of the PLCs and the assignments in general, because once you start sliding a little bit behind, things do tend to pile up. So if you did not turn in PLC one, also the other part to that is if you're enrolled in an online class and you don't turn in any of the assignments, I have to think you're not in the class. So a couple of you have emailed about PLC one and some of the problems and issues. I'll respond to that and at some point today. Nonetheless, I encourage you to keep up on the PLCs and to submit labs and homeworks, because if I have nothing from you by the time next Tuesday comes around, then I'm going to assume you're not in the class and I'm going to drop you from the class. Okay, so just to make sure, at least submit some things. Send me an email saying, hey, I'm trying to submit this, or I haven't been able to, or something like that. But please let me know somehow. If you are intending to stay in the class. And if not, then just do nothing and then leave it to the fates, and the fates will drop you because I am the fate. Um, Other things, PLC 2 is up and going for your enjoyment this week. That is once again a Friday due date, and it's a little bit, there's more on this week's, but they are chopped up into smaller questions. So be prepared. It'll be a little bit of extra stuff to get through, but it still should be about the 1 hour-ish time's worth. All right. So just by way of reminder, PLC 2 is this Friday. Uh, the first lab report, if you have not done your if you have not looked at the first lab, the lab report, oh, right, I got to write bigger. The first lab report is due today, from the lab that I posted on Friday. So that lab write-up and the two corresponding videos that go with it, I posted last Friday. And lab report for that is for today. Homework one is for tomorrow. We'll have an example today and a couple of other things to tie up, and should be all set for homework. But of course, that's not class time, that's by midnight, right? So these things are due by midnight. So you get the extra time of being able to work on it over the evening. All right, so please do remember to turn things in. Otherwise, if you have turned in nothing by what's called census date, which is next Tuesday, because Monday is a holiday, then you're going to get dropped from the class. So please bear that in mind. We left off with an example on ice cubes. So let's look at an example of ice cubes into liquid water. Let's do. I got my two ice cubes. They're just out of the freezer. And I'm going to put them into my cup of liquid water. We'll say that the ice cubes are at the ice cube's initial temperature is -15, and the initial temperature of the water, the liquid water, is 25. So slightly warmer than room temperature, but nonetheless. Let's see. So we're dropping that into liquid water, and it's the liquid water. So that's 30-gram ice cubes, and the liquid water is 200 grams worth. 200 grams. Okay, so that's about 8 ounces worth of water. And I'm going to put in two 30-gram ice cubes. And we're going to basically, the question is, what is the final state? What that means is we have the task of attempting to figure out, okay, what has happened to the ice cubes and what has happened to the liquid. In other words, we don't expect them to stay at their initial values. They are going to exchange heat between one another. All right. So our first duty is to make sure that we put this into an insulated container such that they only exchange heat between them each other and not with the environment for right now. Okay. So we'll start off with heat only exchanged between the two. And this goes into this may take a couple of different forms. It might say I have an insulated container, and then I would kind of assume that this is going to be true because that means heat would not be leaving or entering. We're assuming that they're going to exchange the heat between each other, and that means that because the water, the liquid is 25 and the ice is -15, well, the ice is going to heat up. The liquid is going to cool off. Its temperature is going to drop. So I guess the question is, when you think about what's the final state, there are many different possibilities, right? So as part of this, I'm going to draw you a heating curve, right? We kind of went through this a little bit last time, where if I think about what could happen to the ice, for example, there are more possible things and less possible things, but let's just try to examine all of the possibilities. So one of the possibilities is that the liquid takes so much heat, right? Remember, it has a specific heat to it, and the specific heat tells us by mass how much heat does it take to rise the temperature by a centigrade. Well, or change the temperature by a centigrade, I should say, not necessarily raise it. But this has 25 centigrades. So the question is, what if the heat that it supplies doesn't cause its temperature to change that much? What if all the ice heats, right? Its temperature increases to 0. It then all melts, and then all the rest of the temperature of the now liquid water rises to like 23 or something like that. Right? Not probably possible. Well, not probable, but okay, what if this is a final state? What that means is I've taken the ice from a temperature below 0 centigrade. It has warmed up to the phase change temperature at 0. Okay, so this is ice, and its temperature is increasing. As it goes from here to here, it's changing from, you might say, solid to liquid. Right? That's this transition here. And at that point, it starts to rise in temperature again at a different rate. Okay. But nonetheless, okay, this is a possibility. What if the ice does all of those things. Or on the converse, what would happen if the liquid dropped in temperature, came down to the freezing point, froze, and what if the ice was still at -5 centigrade? Oh, then all of this ice would then drop down to that, because the only time that heat stops transferring, right, is when temperatures should be equal. Okay. The thing that drives heat transfer is a change or a difference in the temperatures of the two objects. All right, so we're thinking about what could be the final state. Just to diagram some of these possibilities out for you. Suppose that, for example, the water has so much energy to give up. All right, I'll just call this the liquid. So here's the liquid energy bar chart, and it's going to go into, for example, raising the temperature of the ice. What if that's only this much? This would be ice temperature up. And then what if the ice was then melting? Okay, well, that would be more. What if the ice then melts and it's this much? And then what if there's leftover even to warm the ice out from 0 centigrade? Okay, well, then we're going to say, well, this is the new liquid. Temperature increasing. Okay, so, right, the question is, we don't know what's going to happen, but we have to investigate what the final state is. There are many possibilities. On the other side, I could have said, well, the ice has a lot of energy to give up, and it's going to actually cause the temperature of the water to come down, and it's going to freeze and all this stuff. So I could draw bar charts for that as well, but ultimately, we don't know what's going to happen, so let's investigate. How should we investigate something like this? Well, one way to do it is to find out, well, I expect the ice temperature to rise and the water temperature to drop. Okay, now just kind of based on the masses and our knowledge of the specific heats. Note that the ice in the solid form, the ice specific heat is rather low. It's about half compared to what the liquid specific heat is. Therefore, as the ice temperature increases, the liquid temperature is going to drop, but not as at the same rate. It's going to drop slower than the ice temperature is going up. Okay. Couple with that the idea that I've got only 60 grams worth of ice here, and I've got 200 grams worth of liquid. So I'm gonna suggest that I'll bet you that the ice reaches its melting point, 0 centigrade, right? And maybe, I don't know if it melts all the way or only melts a little bit, but why don't we figure out something like how much heat would the liquid have to give up in order to reach 0 centigrade? And then we'll have kind of an idea of, all right, compared to that number, how much are we dealing with? Okay, so let's figure out what would it take to get the liquid, all 200 grams of the liquid water, all the way from 25 down to 0 centigrade. And then we'll be able to compare. We'll for the example then calculate what does it take to get the ice temperature up from -15 to 0. And then we can compare those two and just see where we're at. Okay. So let's start with this. Speculations. So let's just get rid of those for now. What I'm going to do is find how much would the does the liquid lose in order to become at the zero, at freezing temperature, to get to 0 centigrade. Okay, so what that is, we'll just call that Q water. That's going to be Well, I probably shouldn't call it water, should I? Maybe I should call it liquid. Nah, I'm gonna call it water. I like that. I'm always gonna do that, so no bother. Okay, and then when we get to the ice, I'll call that with a sub I on it. So how much is this gonna be? Well, we can actually calculate this number. All right, it's gonna be 200 grams worth of liquid, 4 point approximately 2 joules per gram centigrade, and 25 uh, centigrades. And if you are keeping track at home, you'd say, wait a sec, missing a minus sign here? Yeah, there should be a minus sign in front of the 25 because the final is 0 and the initial is 25. What does that minus tell us? Well, it tells us that if I look at my cup full of water here and I look at the ice cubes here and here, if I'm thinking about heat, well, heat, it goes that way, right? And into the ice cubes. It's leaving the water, and that's what the minus is telling us. Okay, now, if I'm going to take a look at this, this is a number that, let's see here. This is a number that we could probably calculate, so let's just do that here. 25 and 200, that's going to be, that's 200 and that's making that 50. So I got 5,000 here. I got to multiply the 5,000 times 4, 20,000, and I need an extra 0.2 on the 5,000. So that's an extra 1,000. So this should be about 21,000. It would need to lose 21,000 joules. I'll keep the minus sign, but it's going to lose 21,000 joules worth of energy in order to take all of that liquid and drop it down to 0. Okay, let's find out how much heat the ice needs to go from minus 15 up to 0. All right, so the amount of heat needed for the ice to go from minus 15 to 0, we calculate that the exact same way with ice temperature, ice mass, and specific heat of ice. And the specific heat of ice, what do we have for that? It is exactly half that of water, so it's pretty easy to remember, 2.1. We calculate this number out then. We go for 230-gram ice cubes, I get 60 grams total. I get 2.1 joules per gram centigrade here. And we go 15 centigrade here. 15 times 6, that's going to be 90. Is that right? Yeah, 90. And I need an extra 0, so that's 900 times 2 is 1,800 plus 10% of the 900, which is 90, so 1,890. So this will be 1,890. Okay. Say about 2,000. All right, so pretty fair to say, yes, the ice has attained 0 centigrade, and there's plenty left over for the liquid to give up. It's probably only dropped by like a couple of degrees here, okay? All right, so we know for sure ice reaches 0 centigrade. The liquid water has dropped somewhat in its temperature. What happens now? What do we have left over? So this is 21,000 and this is 1,890. So we're going to say that it's 20,000 and 890 left, which is 800. So we're going to have, how much is left? 20,000. We're going to have 19, 2, 110. 10. Let's see if I add 90 to that. It goes to 19,200. Is that about right? 1910 joules left over. All right. Now what we need to investigate is the next thing that happens in the ice would be melting. Okay. Sorry. The next thing that happens with ice, it would be the melting. So let's investigate the melting. Remember, this is now what's called a hidden heat. This is a latent heat. Okay. I'm going to get rid of this now. I'm going to go up here. And this. Okay, so let's examine the ice melting. The ice melting is a hidden heat. Okay, this happens at 0 centigrade the entire time because it's a bulk process. And this is the latent heat. And that means we're going to use Q equal to ml. Which means we need to know what is the latent heat of melting or fusing or whatever you want to call it, latent heat of melting for ice. And if you don't know that number off the top of your head, it just so suppose that it's 333 joules per gram. So that's to melt ice, and that would also work the same way backwards. If I was taking the liquid and attempting to freeze it, it would require the same amount of heat removal. Okay. Now, why don't we calculate how much heat would be required to get the ice to completely melt? So for complete melting, I'm going to calculate all 60 grams here for ice melting at 333 joules per gram. And I'm going to come up with, well, this is going to be pretty close, right? So if it's 60 times 300, that'll be 18,000. And I got an extra 33 on the end of that. So I'm probably going to be pretty close to this number, right? Let's see here. So if I go 60 times 300, that's 18,000. And then I need to put on 18,000. And then I need to put in another 1,800 and then another 180. All right. So it's a bunch of eights and ones. 19,980 is what we have to put into the ice in order to get it to fully melt. 19,980. So that's more than the liquid has to give up. So right away, I can tell you the final temperature of this has to be 0 centigrade because the ice has not fully melted. And that was the amount of heat necessary in order to get the liquid water all the way down to 0 centigrade. Yeah. So the ending state is going to be cold 0 centigrade liquid water with 0 centigrade ice left in it, a small chunk, a little bit, not all of it, it's not all gone either. There's going to be a small bit of ice left over, and they're both going to be sitting at 0 centigrade, and the process is going to stop because they're both at 0 centigrade, so no more heat's going to exchange. Okay. Question is going to be how much ice is left over that didn't melt when the whole thing's temperature got to 0 centigrade. All right, so this means that the ice does not fully melt. Now, I mentioned this, I think, in the last class that you could certainly set up a full energy balance equation and try to solve for things. I just find it more, say, straightforward to just start calculating things, especially in a problem like this where you don't know what's going to happen and you just have to find out. it's easier to see, at least for me, it's easier to see what the possibilities are if I calculate it in small steps. Say, okay, how much does this need? How much does this need? How much does that need? And you just compare and see how it goes. All right, so I've got 19,980 necessary. I was able to supply 19,110. Right, so I'm gonna have 870 left over. That means okay, so that means I'm going to take the 19,110 because that's the amount of heat that was able to be supplied to the ice. I'm going to say, all right, Q equals of the ice is equal to mass of the ice times L. And what I'm asking is, given this amount of heat and given for every gram I need this much to melt the ice, how much ice melted? Okay. So what I'm asking really is how much ice is melted. And I'll be able to solve for that by chucking the L underneath here. And then if I want to know how much is left over, all I got to do is subtract that from 60 and I'll know. All right. So this will be 19,110 on the top and 333 joules per gram on the bottom. And this will be the amount of ice that melted. All right, so if you do that, you're going to end up with 57.4 grams of ice that must have melted. And I suppose that leaves, sorry, it said I was going to write larger. It's going to be a constant battle to do that. So that's going to leave 2.6 grams of ice left. So depending on, I don't think you really want to go into this. Maybe I've got 1.3 grams. Nah, I just got 2.6 grams of ice left. And it is at 0 centigrade. Rule of thumb is if you have a multi-phase mixture, and by multi-phase, I mean ice liquid or liquid steam or right, two phases of the same thing. And they are, one is actively in contact with the other. Maybe one was turning into another, but didn't quite make it all the way, like in this one. Then the final state is going to be the phase change temperature. Okay, so this ice heated from 15 below to 0 and began melting, but did not fully melt. The liquid that it was submerged in dropped all the way to 0, but did not start freezing because at the point of time in which it reached 0 centigrade, there was still ice there. Right? Now, if the ice that was left was less than 0 centigrade, then you could have said, well, possibly the 200 grams of liquid might have started freezing. But I can't say that because the ice that was put in there came up to 0 centigrade, the liquid dropped to 0 centigrade, and now there's no more heat transfer because they're both at the same temperature. All right, so there's 2.6 grams of ice left at 0 centigrade, and there's 200 grams of the original water is also at 0 centigrade, along with the 57.4 that melted, right? So total amount of water at 0 centigrade, total amount of liquid water at 0 centigrade is 257.4 and 2.6 grams left in the solid phase. So that's the original water at 0 centigrade, that's the ice left, and that's the final state. Alrighty. So that's how you deal with phase changes between between multi-phase systems. Like I said, I don't require that you do it this way. Maybe you're gonna think of a better way to do it. This is just the way I think about it because I like to see how much am I working with. So I try to get those numbers put out right away and just to kind of figure out what's going on. And I'll just reiterate again, you can set this all up algebraically. It just turns into a big quagmire and you don't get anything useful physically out of trying to manipulate the equations and solve for them. If you like a challenge, hey, go right ahead, be my guest. It's just going to take a lot of time and effort. And I don't know whether you'll be happy at the end or not. I can tell you that I probably would not be. But anyways, that's beside the point. Okay, so what we're going to do here is I have one thing left to talk about, uh, which deals with a homework problem. And so that will be the proof of uh, that will be the proof question that I forget which number it is, maybe 10 or 9 or 6 or I forget. But after this, then I think that's enough for the homework that is assigned. And we're going to then move into talking about temperatures and thermal expansions and go on to what's going to be on the second homework set. All right, so let's get this taken care of. Any questions about this stuff? No? Okay. Okay, so let's take a look at allowed and forbidden cycles. And how do we use this to say what can exist and what can't? Okay, so this is allowed and forbidden things according to the first law. Now, what I'm going to do is I'm going to denote a cycle as a circle. Right? So a cycle is going to be something like this. And then and before I go on, what that means is if I look at a PV diagram of a cycle, what it means is I started at a particular set of state variables with my system, and we'll just assume it's an ideal gas. And I went through a couple of different processes such that I have reestablished the initial variables, the initial values of the state variables. Okay, so for example, maybe I started here. Well, you can't see that. So maybe I started here like that. And then I went this way, and then I went this way, and then I went this way, and then I came back this way. Right? But that's a cycle. I've gone through different pressures, volumes, and temperatures, and I am now at the original values. Okay, so I'm going to denote that as a circle, meaning I've completed one cycle. So things that are allowed by the first law. Now, I know I gave you a little bit of second law insight, but we're not there yet. So this is just allowed by the first law. I could take a cycle in which heat was transferred in and work was transferred out as long as and I'm going to put Do you want me to put magnitude bars around these things? As long as Q equals W. I've got the arrows on here, so I don't think I need the signs. I don't need to worry about the signs. You can tell that the work is being done by the system and heat's coming in. What this is saying is, as long as those two are equal, that's allowed by the first law. Likewise, what would be allowed by the first law? Let's do it let's do it this way. Would be this, and it'd be the same. As long as Q and W were the same, then you could supply work to something and heat could get transferred. Okay, so this would be along the lines, not exactly, but it would be along the lines of something that is a refrigerator. And these two main ideas, the idea of an engine which does usable work for us and a refrigerator which consumes work but affects a heat transfer for us. These are going to be our two main models. Okay, so what might we have that would be forbidden? What we have that's forbidden, if I look at these, I could take this and say, let's go do this. There should be no uh, there should be no possibility for this via the first law, right? This is a situation where heat is leaving, heat's coming transferred out, and work is being done by the system. If this is truly a cycle, what does the first law tell us? It tells us that the change in internal energy is zero. Right? That's the essence of a cycle. And that means that Q plus W should be zero. And in these cases, it would be, as long as these two are equal in magnitude. Q coming in, W leaving, this would be a positive Q and a negative W. And that would, as long as they were the same magnitude, that would satisfy first law. That would also satisfy first law as work coming in as positive and Q leaving as negative, same magnitude, satisfies the first law. This situation will not satisfy the first law because these are both positive quantities. And that means that I'm going to add Q plus a W and get not zero. So this would be explicitly forbidden by the first law, and likewise would its counterpart, which goes the other way, like this. And work in that way. All right. That would also be forbidden because that means it's taking in heat and it's taking in work and its internal energy has not changed. That does not make sense from a first law perspective. Okay. So what I'm going to do is I'm going to use these two, these allowed and these prohibited, to establish that it's not possible that a closed cycle does nothing else but work. So in other words, I'm going to try to establish the idea that there cannot be a single flow cycle. Single flow meaning I've got only one of these. Okay. The essence of thermodynamics is then trying to use what we know is allowed and prohibited in order to forecast what else is going to be allowed or prohibited. So let's take an idea here. And let's suppose, and this is going to kind of mimic the reasoning that I was looking for on that homework problem. I'm going to suppose by assuming the contrapositive, which is to say I'm going to take one of the allowed cycles and I'm going to assume that it's actually possible that, for example, maybe the work that I'm extracting from the cycle is slightly larger than the heat that I'm putting into it. Okay, so I'm going to take an allowed cycle and tweak it so that it's not allowed. And then I'm going to put it together with another cycle and say, oh, well, if I take this thing and this thing, what else is not allowed? Okay. So, for example, uh, let's go over here. If I take this first one here, in which I am going to say heat coming in, Q, and W leaving, right? I'm going to shorten that Q arrow so it's small and the work arrow is larger to tell you that actually the work coming out is larger in magnitude than the heat that's going in. So I am contravening the first law here. W is greater than Q. First law explicitly says that this is not possible. Okay. Well, if it were possible, what would I be able to do? So what I'm going to try and forecast is something else that's not possible. I'm going to take something that's not possible, combine it with something else that is possible, and then say, what else is not possible? I'm going to take this thing here and I'm going to combine it with its cousin, its sibling, this one. I'm going to combine it with this one. And I'm going to say, well, now take some of that work, call it W prime, and I'm going to put it into this one. That means I'm going to eject heat out of it. And in this one, I'm going to call that Q prime. So I'll call these ones the primed quantities, and these ones are the unprimed quantities. Okay. In this one, I'm going to say W prime equals Q prime in magnitude. Okay. In magnitude. Even though I made the arrows not quite the right size, so I'll just change that one to be slightly smaller. Okay, like so. So what I'm doing is I'm taking a forbidden thing and combining it with a not forbidden thing. If I were to do this, note that the work I'm putting in the work I'm putting into this one necessary to eject Q prime is less than the work that I'm getting extracted from this cycle here that required Q to start it. Now I'm going to make some cycle adjustments, and this is where the proof kind of goes in, and this is the same type of reasoning I'm looking for on the homework problem. I'm going to say that ultimately what I want to do, I want to adjust these two cycles such that Q and Q prime are exactly the same. So I'm going to adjust Q prime to equal Q. That means that if I combine these two things together, there is zero net heat transfer to the environment. The first one took in some, the second one rejected some. I'm going to say, let's make them the same. I'm going to adjust my cycles. I can do this. There's a proof of that too, but I'm not going to show you that. I'm going to adjust the cycles such that Q and Q prime are equal. Then what do I have? I have a situation in which my overall full cycle looks like Q coming in, Q prime leaving, like so. Okay. A lot of work coming out, or maybe not a lot, but I guess whatever's left over. I'm going to go a lot of work coming in, W, and a little bit, I guess I made that a little bit too big, maybe like here. And this is W prime. Oh, no, whoops, sorry, got those backwards. I got those backwards. There we go. Like that. All right. So I have a net heat of 0 in or out. The net heat is 0. The net work is equal to W minus W prime. right? That's a work that was a work that was done, and then work that was required, work that was expended, or I don't know, whatever. Anyways, we got work out of this one, and I'm taking some of it and causing this one to happen. But now I've got work left over. So the diagram that this effectively looks like, right? What does this effectively look like from a thermodynamic sense? It looks like it looks like this, where I've undergone a cycle and I'm extracting usable work. And there's no net heat transfer in or out. This is explicitly forbidden by the first law because I can prove that I took something that was explicitly forbidden by the first law and said, well, if I combine it with this that's not forbidden, this is an allowed one on the side here, this is allowed, then what I'm going to get is something that is not allowed. Taking not allowed plus allowed gets me not allowed. Okay. So this is not allowed because I go back to my initial premise and I say, oh, well, that wasn't allowed, so this shouldn't be either. And that's the kind of reasoning that I'm looking for on that homework problem. You take the contrapositive of the initial thing and you try to say, oh, how do I say that I take something that should be okay, tweak it so that it's not, follow the logic through, and then all of a sudden I arrive at this thing, but I can't have it because I can't do the first thing. It's a situation of yay, darn. All right. So yes, I can prove that this is not allowed by the first law, and you probably knew that already because that would violate the first law, right? I can't just have a cycle with energy coming out. Likewise, what else is not allowed? I could show you using the same type of reasoning that this would not be allowed, right? A cycle with work coming in. This would not be allowed. A cycle in which heat is leaving. This would not be allowed. A cycle with heat coming in, right? I can basically deny all of these single flow is what I call them, single flow heat and work cycles. You can deny those by making arguments like this one. Okay. All right, so that's a little bit into the insight of the logic and reasoning that thermodynamics affords us. And I think that's enough for us to be getting by with the homework. So homework due Wednesday. There'll be a quiz enabled on Canvas on Wednesday. You'll have your pick of time in which to do it, but I do ask that you sit down and do it all in one go, not starting and coming back to it after a couple of hours and whatnot. So make sure that you pick a time where you can sit down and spend an hour. If and that's more, it should be more than enough. But remember, that's also going to include upload and download times. So whatever it takes to get the quiz to you, clock will have started. Whatever it takes for you to take the photo and upload, that's already built in. Okay, so the time is whatever you have left over from that. Okay. Okay, let's take a look at temperature scales. Something I put off a little bit because I feel like we don't necessarily need to talk in depth about it. It's kind of something that you probably already have a fairly good awareness of, but nonetheless, I'll just go ahead and put some thoughts to it just so that we're all on the same footing with regards to the temperature. I have alluded to this in previous classes, and that is that it took a long time for people to figure out what the temperature is, like what the meaning of it is, how to construct a temperature scale. It's not as straightforward maybe as you might think. Well, let's take a look at this. Fahrenheit spent most of his life trying to figure stuff like this out. So let's take a quick look here. I mentioned in our talk on day one that there's something known as the empirical temperature, and there's something known as the thermodynamic temperature. Right. Um, Again, I still have to remember right here. The empirical temperature is allowed by the zeroth law. The thermodynamic temperature is kind of more or less defined or weeded out from the second law. Okay. So we haven't talked about that yet, but nonetheless, I'll just, and we might a little bit as time allows, but ultimately, unfortunately, this class is about results, not about process. And this is one of the reasons it's a hard class to teach. Nonetheless, the differences here are the empirical temperatures are things that you are very well familiar with. This is the degree Fahrenheit or the degree centigrade. Okay, these are the temperatures that are based on a say a thermal equilibrium with a third body, right? This is the idea that I can take a thermometer which has mercury in it, and I don't know if I'm even allowed to talk about mercury anymore. But nonetheless, I'm going to take that mercury thermometer, I'm going to put it in something, and I'm going to watch the volume change. Okay, so I'm using the observable change in the state of the mercury to infer a temperature of this stuff. And in order to do that, we need reference temperatures. Okay, we need reference temperatures, which means that because of the usefulness and abundance of water, we're just going to say that freezing and boiling are calibrated to water, right? And so on the Fahrenheit scale, you would freeze water at 32 and boil it at 212. Whereas on the centigrade scale, you would do the exact same things at 0 and 100. And these are empirically based temperatures such that they are monotonically increasing the entire time, right? No temperature scale goes like this in the mid, right? You don't just increase the temperature and all of a sudden, no. If you're going heat added, it's always going up. This is based on the idea, like I said, that if I had a cup of hot water, then what I'm going to do is I'm going to put my mercury bulb thermometer in here, and I'm going to watch as it goes. It doesn't go all the way up to there. It goes up to there, right? Which is an expansion. Say outside the hot water, this is hot. Outside the hot water, it was only here. Right? So we're going to say these are different temperatures because the volume occupied by the mercury has changed. This is a typical thing of materials in which if you heat them up, if you increase their temperature, they get bigger, spatially larger, okay? And that is known as thermal expansion. It's based on the thermal expansion, and in this case of mercury or alcohol thermometers or whatever it is. Now, the thermodynamic temperature scale, I'll cut to the chase on this one, is simply the Kelvin scale, or if you like, the absolute scale. If you're not familiar with the Kelvin scale, there's also the Rankine scale. If you prefer Rankine, you can use those instead. That's also an ultimately thermodynamic temperature scale. Freezing on the temperature, freezing water temperature on the Kelvin scale happens at 273. and boiling happens at 373. What you're noticing then is that really a Kelvin degree and a centigrade degree are the same size because it's still 100 between these 2 points. It's just that the zero has been shifted. And the zero of the absolute scale is due to kind of what we were investigating in lab last week slash now, I guess, really, right? You're looking at something like this. Where if it's an ideal gas, you might have a pressure versus temperature scale, say plot, and you might take a bunch of different gases, right, and plot these out so that I get one of these coming down to like there. I get this one here. I get this one here. Right? They're all kind of arriving here. This is the temperature at pressure equaling zero. And this is the thing we were looking for in lab one. That temperature when the pressure equals zero is the lowest possible temperature of an ideal gas and turns out to be the basis for the thermodynamic temperature as defined by a slightly different path. Nonetheless, any ideal gas that you take pressure temperature data for should extrapolate down to approximately this region down here. And that's what our goal was with the air last time, okay? All right. If you are interested, the Rankine scale, I mentioned the Rankine scale. The Rankine scale has the same temperature degree size as the Fahrenheit scale, but is basically the absolute scale on the Fahrenheit with Fahrenheit degrees instead of centigrade degrees. Since mostly everybody uses these, we just stick with centigrade degrees. But if you're interested, freezing on the Rankine scale would be 492. Oops, I put centigrade. It's going to be degrees R, 492 degrees R. And then this thing is 180 more. So you go to 672 degrees R for the boiling water on the Rankine scale. Fun times. A little bit of trivia there for your next cocktail party. What do you suppose it is in here? Gosh, I don't know. It felt like 500 Rankine this morning. What do you think? It's a good icebreaker. Or it's not. That's the case may be. I want to explore thermal expansion a little, just a touch more here, and then I think we're probably going to be just about ready to end. I want to consider, in order to make life a little bit easier as we are learning this, I'm going to consider thermal expansion, but only in one dimension to start off with. Think about 1D thermal expansion. Let's this comes out of a thinking once again that is a little bit outside of thermodynamics, at least classical thermodynamics, in which we think about what materials are made out of and what they do when their temperature increases. Okay. So let's take a material. Actually, let me back up for a minute. Most materials are constructed such that the atoms form a lattice, and right now you're understanding why this is outside classical thermodynamics. I just said the word atoms. is a lattice work of atoms. And you can perhaps imagine taking it like this and then building up a cube worth of this stuff or something like that, right? Taking one like this and then stacking the planes this way and that way, such that you had a crystal. Okay. So let's assume that we have something pretty straightforward like a square lattice, which they are all square. But let's assume we have something like that. And we're going to take the size in one dimension to be much larger than the size in another dimension, such that we can kind of neglect the expansion. Make no mistake that this is a thermal expansion approximation, because everything always expands in all directions. We're just assuming that the dimension that one of the dimensions is longer and will exhibit more of the expansion than the others. So we'll ignore the others. Okay. Let's take something that is longer in one dimension than in another. So what I'm going to do here is I'm going to draw. Let's see if I can. Can you see if I make dots like that? Okay, that's not showing up too badly. What I'm going to do is I'm going to draw an object which is longer this way than it is this way, and we're going to consider the expansion along the horizontal direction. Okay, so here, I'm just going to arbitrarily say I've got this much. How many do I have here? 4 and 3. That's not going to work. I need 4 and 4. Oh, not that one. Okay, there we go. Okay, so I've got atoms in an object. Okay, whatever they are, what doesn't matter. Okay, just something that's kind of long and thin. Okay, and I'm going to tell you that this right now is at some temperature T. It's at temperature T right now. And what I'm going to do is I'm going to add some heat to this, and I'm going to increase its temperature slightly. And what's going to happen is it's going to expand just ever so slightly. Because if we think about what's happening on the atomic scale, when you increase the energies of these things on the atomic scale, and we, by the way, have only talked about the ideal gases, so we don't really have a good feeling for what happens when something's bonded in a solid or something like that, right? Like I showed you this thing here. It's got springs between them, right? There are springs here between these things. Well, okay, maybe they're spring-like or something they're holding. So if I increase the energies of these things, we know that they're going to do two things. One of them is the kinetic energy could increase, and the second thing is the potential energy could increase. Okay, so the potential energy is related to the bonding energy. Okay, and the kinetic energy is related to what we have kind of been calling the thermal energy. So not only are they going to be moving a little bit faster, they're going to be taking up more space as I increase the temperature. So suppose that I increase the temperature, excuse me, and I hold the left side of this fixed. Okay, so now here I'm going to go to T plus a little bit, plus a delta T. Right, I'm going to take these here and I'm going to keep them here. I'm going to go, say, 1 here and 1 here. Okay, so T plus delta T. Actually, you know what? I'm going to do that further down. I don't like it there. I'm going to do this down here. All right, so I'm fixing the left edge of this. I'm going to say, suppose that each little, say, square, right? I basically have a couple of squares kind of attached to each other. Each square gets bigger by, say, well, say 25%. I have grid lines on my board, so it makes it easier for me. If you're using ruled paper, then that's great, graph paper. So I'm going to say 25%. That's going to put my first one over here to right here. Okay. Now, what that does is since this one shifted that way, this one here is also going to shift that way and it's going to expand. So now I have to not only go over two, which is the spacing, I have two boxes between each line here. I would go 1, 2. I also have to go to here, the extra 25% expansion. So by the time I get to number 4, I'm going to go 1, 2, and I'm going to have to be here now, like that. Is that right? I have to shift over a full, yeah, right? So 1 is staying here, 2 is there, row 3 is here, row 4 is here, and you can see what's happening, right? It's growing larger with every subsequent square, with every subsequent set of stuff that I'm putting on here. Okay. So now, let's see, this one had to go, this one expanded by, wait, did I get this right or am I wrong here? This one expanded by that. That means that this one went over 1, 2 and expanded half. This one had to go 2 and expanded 1. And now this one has to go over 1, 2 and expand another one here. So now it's going to be out here. Right? They're getting subsequently larger and larger. Okay. So what's happening is the amount of expansion that's happening with this piece here is dependent on how long it's dependent on its original length, right? Because if I had none of this here and I just started just these two columns of atoms here, it would have only expanded a little bit. But now, since I'm all the way out to here, look how much more it's expanded since I kept adding on extra. Okay. So the expansion, this tells you that the amount of expansion is dependent on what the size of the thing is. Okay. It depends on the original size of the object. So that when you think about smaller things like, I don't know, for example, this pen here, if I heated this up by 10 centigrade, it would get longer. Okay, great. If I thought about the Golden Gate Bridge and heated the Golden Gate Bridge up by 10 centigrade, it's going to get a lot longer because it's longer to start with. So each little bit of it expands the same amount, which causes everything to kind of build, it compounds, right? It's essentially a compound interest problem. What that means is I can set up, oops, I can set up how this happens mathematically. In other words, the rate of increase, depending on the length, is some amount, depends on the material, right? This is a coefficient that is material dependent as I bump the temperature up. This thing here is called the coefficient of thermal or linear expansion. Okay, and if we make this not differentially small, then we can work with it in macroscopic size bits. Okay, so in other words, if I unlimit this process and I say I'm going to let the amount of change of the length become some measurable amount because I have let the temperature become some measurable change, then what I end up getting is that the change in the length of an object is proportional to the original length of it, right? L naught times the coefficient times the temperature change, right? So this is not really here. This is coefficient is this thing. This thing here is the original length. This is how much the temperature has changed. And as a consequence of the temperature changing and the length and the coefficient, this delta L is the total change in the size of the object. That's the object's change in length. Okay. Note the units of alpha. The units of alpha are going to be per centigrade because this is a length unit. This is a length unit. So I'm already taken care of with lengths. I've already matched my units. All the rest of this stuff then has to become unitless. That means alpha times the temperature change has to have basically no dimension to it. Right? Coefficient of linear expansion, the units of this are 1 over degree centigrades. Or if you like, 1 over kelvins or something like that, okay? Such that when I multiply by whatever temperature increase I have or temperature decrease I have, then I get no units from the alpha times the delta T. I'm going to leave you with this one thought here on what this is actually telling us, because this is a pretty good punchline to this argument. Okay, so this is giving us information about the potential energy function of bonding between atoms. Again, not a classical thermodynamics topic, but something that's very interesting. If the bonds were truly spring-like, a spring potential would be, if you remember from 4A, right? A spring potential energy is elastic potential energy. And it would be something like 1/2 K times delta X squared. If I graph that, it's a parabola, right? It's an X squared, that's a parabola. Looks like this. So as I increase the energy in this parabola, what happens to the average position, right? The average position never strays from the middle, because as much energy as I add to it, all you got to think of is a marble rolling up and down this bowl, right? If I have the little thing oscillating like this, it goes like that. If it's like this, the average position is still right in the middle. Okay? There is no expansion as I increase the energy if it's a spring-like potential. This is telling us that the bonding between atoms is actually a little bit more complicated than springs. It actually is going to end up looking like this. Like so. It's going to end up having a tail on it like that, because what that means is as I increase the energy, note what happens to the average position. The average position starts down here as I have just a small back and forth. But now as I go up to an energy up here and it rolls from here to there, notice it's going to spend a lot more time here. So the average position is going to shift it to over here. Okay? So this is telling us that the atomic bonding potential energy function is not simple like a spring, but is in fact a little bit more complicated. And those are little fun offshoots of investigating thermodynamically what happens when things are heated. And with that, I will leave you this class. You hopefully have enough to get on with the homework. Remember to please turn in materials. And I had one last thing to say. I think problem 12, I left off something. I left off something about problem 12, which is the spring and the pressure. I forgot to mention that in the pressure side, right? This is a situation where I have a piston connected to a spring. I forgot to mention that when it's at equilibrium, this dimension of the gas pressure, I just called it some distance L naught. So you can use this when it's at equilibrium, right? When this thing is at equilibrium with the spring, and you investigated this in part A, right? The pressure on this side is P naught, and the spring is compressed by delta L. When that's true, this dimension is L naught. I forgot to tell that to you in the problem. I don't know how that one escaped me, but oh well, so much for rewrites. Uh, so any questions on homework, fire me an email, and I hope you have a good rest of your day, folks. I will talk to you tomorrow or whenever it is that I see you next.